The Python script is self-cal score tutorial.py. Yeah, so make sure to follow along self-calibration. Open another script, which is also in the GitHub page. So you can do copy and pasting. Now we're going to do self-calibration. But before I start introducing self-calibration, I want to quickly introduce the concept of just doing calibrations. So we know that interferometers are measuring the visibilities, but in most of the cases, the true visibility can actually be corrupted by many effects. So you can imagine, like for each individual antenna, they will be affected by atmospheric attenuation. The seeing may not be good, and even there are variations in the electronic devices, like in gain, delay, and phase changes. So, and this is just for individual antenna, but you can imagine, like, if we are doing the baseline interference pattern stuff, there are also problem on like maybe correlators, the like interference signals, or some noise in the radiometer. So, so doing calibration is the effort to measure and remove any atmospheric or instrumentation variations that may happen. And they could depend on either time or frequencies. So here I'm listing some typical steps for calibration. So first of all, we definitely want to correct for frequency-dependent telescope response, which we call the bandpass calibration. And we will select a calibrator on the sky for this. And we also want to remove effects of atmospheric, like water vapor, or any time-varying phase or amplitude change due to atmosphere. And this is called the gain calibration. And finally, we definitely also want to set the absolute flux scale to make sure they are on the consistent flux scale. This is called flux calibration. So we actually don't have to worry about this for proposing observations, because ALMA actually take care of all of this for us. So you just need to worry about your science observation, and then they will pick suitable calibrators for doing all these calibrations. So this is because they already have a list of calibrators for ALMA and actually for VOA as well. So these calibrators are usually bright quasars or solar system objects. And this is because those objects have well-known flux and structure. So this means we have a good model, like knowing how their flux should fluctuate, or like how their phase changes or amplitude changes should be. And so, so for example, the image here on the top is showing some measured phase. It can be very messy. And the image on the bottom is our phase model. In this case, it is based on the calibrator 36138. So with this model and the measured calibration, the measured visibilities, we can then get a corrected phase, which is shown on the right figure here. So using a model, we can determine corrections to make the data to look like what we should expect. So the essence of calibration is that anything can be calibrators. It doesn't have to be the quasars or the solar system object. If we have good models on some sources, then it can also be a calibrator. So this is what self-calibration is doing, actually. So we have learned doing T-clean, and we know that T-clean would also create a model for our source. So this means that if we trust our T-clean model, then we can use it for self-calibration, actually. But of course, this relies on the assumption that what we clean is real. So for example, here I'm showing a funny example that, so this is our dirty image, and you can see this is definitely the source in the middle, right? And we know these are probably from point spread function. But if we somehow decided that, oh, I think this one is probably the real signal. So instead, I set a mask around the signal and start doing the cleaning. Then finally, our model, like our final recovered image would look like this, which is a completely fake structure because of our incorrect cleaning. So be cautious that self-calibration only works when we have very good signal-to-noise data that we trust the bright sources at least. So, so the reason for doing self-calibration is that we want to improve sensitivity as much as we can. So this is particularly good for a telescope like ALMA or VLA because they already have very good sensitivity. So usually the image we have, like if the brightness spans a wide dynamic range, then we could pretty much trust the high signal to noise part of the image. And in this case, we can use it to do self-calibration and push the sensitivity to reveal even fainter structure. So you might think that isn't like, is self-calibration then a circular trick that because we believe what we cleaned, then of course the source will look like what we think it should be. But it's actually not the case because, as I said, we need like huge dynamic range on the brightness, and we need to have good signal to noise to do self-calibration. So if you don't have good signal to noise data, you shouldn't be doing self-calibration. So this is only for already good signal to noise data, and you want to push the sensitivity to even further. So, and the reason why ALMA can do this is because, you know, like they have a huge number of baselines, like they have much more baselines than the number of antennas actually. So this is actually a over-constrained problem that, because you have so many objects with enough signal to noise that can be used to calibrate themselves and get us a better image. So here's an outline of the self-calibration process. So first of all, we would inspect the data and ensure if the signal to noise is good. If it's not good, it's like 3 sigma, 5 sigma, no, don't do it. You don't need self-calibration. But if it does provide good signal to noise in some regions and a huge dynamic range, we can start to do cleaning and create models. And then we would apply phase calibration first, and then compare with the original data to see if it really pushed the signal to noise up. If it does, we can continue to do amplitude self-calibration and go on. But if it does not, we should also stop. So yeah, so the point is just that to do self-calibration, you have to ensure your data is good enough. So self-calibration is actually now automated in the ALMA pipeline starting from cycle 10. But yeah, so if you have data from cycle 10 or even more recent data, you don't have to worry about this. They will automatically determine if it is good for self-calibration and run the pipeline for you. So there are, of course, some limitations. Currently, self-calibration is not supported for spectral line observations and not supported for mosaics. And for ALMA data older than cycle 3, you will not be able to do self-calibration as well. But I think they are in the progress of improving this and trying to make self-calibration to cover all older data as possible. So here are some more information for self-calibration on the website. Okay, so now would be the hands-on session. So it's our turn to calibrate. So make sure you have your scripts open, the self-tell tutorial.py. And so, so first of all, we should create an image to compare with, to be compared with, because we want to see before self-calibration if it's like really worse than after self-calibration. So try this and do the cleaning again, like the steps we already ran before. So usually two rounds of cleaning with like 1 or 200 iterations should be enough for this. So just to mention, like this command is actually completely the same instead of like now the rating is being set to. So yeah, we could also compare with the image, the continuum image we just construct. But so all done. Awesome. Okay. So yeah, so after, so this should like create images like PSF files called before self-tell.cp. And now we are going to build our model. So we are going to do the first clean to create a model. So we input again the measured visibility file. And so all the commands are actually the same as the previous one, but we need to add save model equal model column. So this would save the model because like we need to use the model for self-helping. So this would be the second tclean command from the script. And make sure you also do cleaning for this. Otherwise, it will just be, we are saving like the 30 image and it does not create model. And let me know when you're done. Things all right for Carl? Okay. Takes a little while. So while everything is still running, I thought like I could go to the next step earlier. So after we create the model, we want to do the first gain calibration. So yeah, so we are using the phase only calibration first. So we are setting setting cal mode equal P. This means phase only calibration. And sol int is the solution integral. We are setting it to infinity as the first time, but infinity doesn't really mean infinite time. It just like ensure the longest time to make sure you have enough signal to noise. And once we find that if the self calibration does work, does improve the signal to noise, we will need to gradually decrease the solution interval time and to see if it still improves the signal to noise. So I see yeah, so there's a question on the chat saying, why do we change the weighting from bricks to natural in self-cal? And there is actually not a reason. You could also do bricks in this case and like directly compare with the previous image we create. So the weighting algorithm is totally dependent on your science goal. So for in terms of like demonstration, it doesn't really matter. You just need to make sure the images you create, you compare with, has the same weighting scheme. Yeah. Is it still running? Oh, you just implemented and okay. Uh, oh, you already applied this? You mean even the next step? Yeah. Uh, yeah. So we need to after doing the calibration tables, we need to actually apply the calibration. So I think this is straightforward. The visibility using the gain table we created based on cal during a linear interpretation. So this should be a quick command, right? Yes. So now we can do the second T clean to since like we have already applied the self calibration, we should do a T clean and we should do a similarly shallow T clean. So if you do like iteration of 500, you should also do iteration of 500 this time. And if you do the interactive stuff, it's like if you clean for like 2 rounds, then you should also do 2 rounds this time. And after cleaning, we will inspect whether the resulting cleaning is better than the image we directly cleaned in the beginning. So everyone done the second paper? Before self-count. So the first image is just to create the model. We're not really using that. Oh, I see Serena is asking, can you explain cal mode, ref, and yeah, so cal mode is the calibration mode, and we set to P because we want to do phase calibration first. So usually the procedure is you first start with phase calibration and then see if it really improves things. If it improves, you proceed with like amplitude and like other calibration. So we do cal mode equal P. You could also do A for amplitude, but I mean, to begin with, we always start with phase only. And ref, and I believe it's just a reference antenna. And gain type is just different ways um to get the gain get the calibration solution. Yeah. And the reason is
Well, then, if you take it as a reference, it doesn't matter who the reference is. Like, let's say you take a reference over there, out there, and that could be imbalanced. So,
so I'm not sure if Serena, you heard this. So Peter was explaining like the reference antenna, we usually select an antenna that is close to the center. Just to like avoid like if you have like less symmetries, like if you have like different distance, like if you are too distant from like some antenna, you might be measuring like different phases. I don't know.
That's something in the center.
All right, so you done? Okay. Okay, so this is actually our last step. So now we can then compare the image. So bring up the before self cal, and after self cal. You should see that some of like these noises would be much different. So again, bring up CARTA and load in these two. Okay, so let's start the introductory part. Okay, so I'm assuming most people have all these all these data and software already. And I do really recommend you open up imagingscoretutorial.py on the GitHub page or download it so that you can copy and paste. So it will be much more efficient.